Welcome back. The last time we discussed why water molecules are able to dissolve ionic solids such as sodium chloride, and that's simply because they're alike. Right? Water molecules have negatively and positively charged ends, and so do ionic compounds. The only difference is that the force that's creating the dipole is stronger in the ionic compound, where the electron is completely pulled away, but the effect is still the same, that we have positive and negative ends and they can interact with each other. So if two compounds are able to interact with each other, they are miscible. All right? And so you can have polar compounds mixed with other polar compounds. Ionic compounds can interact with other ionic compounds, and so can polar and ionic compounds. And so by the same token, things that don't mix are not alike. So nonpolar compounds and polar compounds don't mix. All right? And we know this because we've all seen oil beat up on top of water, I'm sure. And so if you were to mix half a cup of water with a half a cup of oil, you would see a separation. The oil would float on top and the water would be on the bottom, and so they just don't mix. And you can see here an example, C5H12, which is very similar to oil. It's a nonpolar compound. Remember, carbon-carbon bonds and carbon-hydrogen bonds are nonpolar. And so, of course, on the bottom we have water and in red and white, and so you can see the separation here. And that's because they just simply don't interact with each other. And the reason that oil floats on top and the water is on bottom is simply due to the density of these two different liquids. Water is more dense than oil, and so therefore oil floats on top. All right. This is a simple summary slide. We've discussed this in great detail. Of course, the most important part about this slide is that it shows you the increase in strength that holds these molecules together, all the way from the weakest London dispersion forces, which is a super weak force and easy to break, all the way to the dipole ion interaction, which is the strongest. And so there's a large range here between 30 and 100 kilojoules per mole. I just want to remind you that the intramolecular forces, the forces like covalent and ionic bonds, are much, much stronger than any of these intermolecular forces. So the weakest covalent bond is about 140 kilojoules, and the strongest is about 580. The strongest is between silicon and fluorine. It's 580 kilojoules, which is, of course, much stronger than any of these. And so if we're looking at the intramolecular force between water molecules, it's between 10 and 40 kilojoules, or it's 40 kilojoules really for the hydrogen bond that's shown here between water molecules. But of course, the covalent bond between oxygen and hydrogen is much stronger than that intermolecular force. So it's much easier to break that intermolecular force. Okay, so the difference in strength of these forces holding molecules together, of course, dictates a number of effects on the property of solutions. Okay, and so boiling point, melting point, which makes sense, right? So the stronger that intermolecular force is, the more energy you have to put in to get something to boil. And so it has an effect on the boiling point, the strength, because that's by definition what it is. You're boiling something when you're breaking the force between molecules. And so that, of course, can differ between different kinds of substances. The boiling point of ethanol is going to be different than that of water, and so on. But there's a couple of other things, and I'll just briefly have a slide on each of those. Surface tension, viscosity, and capillary action. So I'll just briefly talk about each of those. So imagine we have a lake with water in it, and so we have all these partially charged water molecules. And so what they want to do is they want to neutralize that charge, and so they surround each other. Right? So if you're focusing on a single water molecule here in the center, just represented as a bead, at this point, for simplification, it's going to be surrounded on all sides, not just in two dimensions, but in all three. It's going to be completely surrounded by other water molecules, so to neutralize its charges. Okay, but on the surface, of course, you have exposed charges. So what will happen is that the exposed water molecules on the surface will try to pull down so that they can be surrounded by other water molecules. And so that leads to surface tension. What that does is it creates a thin film on top of that surface, and so you can actually have items that are more dense than water sit on it, right? So the paperclip's really the best illustration here, how you can see where the density is trying to pull it down, but it doesn't sink. And then of course metal is more dense than water, but it's that surface tension, that thin film that is built up due to that surface tension. And there's an application here on the left. If you go fly fishing, and insects that can walk on water do that because of surface tension, right? And so this is related to viscosity, which is just some liquids flow faster than other, and that's usually simply due to, of course, intermolecular forces and then molecular weight, similar to London dispersion forces. They're larger the molecular weight, the slower the flow, and so that's measured in poise. So if you ever see that, poise has units of grams per centimeter times second. These are the SI units, and we just take that and turn it into a poise. So if you see a poise, that's what it's talking about. It's talking about viscosity. And so here is a table of molecules that have an increase in carbon-carbon chain length. So each of these molecules goes from 5 carbon 6 to 7, 8, 9. So we have an increase in chain length, and so we have an increase in viscosity or flow. So that's just one slide here, not super important. Capillary action, however, is very important. Capillary action is how trees feed their leaves with water, right? So you think about it, you've got a large tree, and how does the tree get the water all the way up to all its leaves? It doesn't have a pump. It does that by capillary action. So if you think back to the first semester, if you took this here at STIC, you did a chromatography lab where we took a large piece of paper and we drew a line on it, and we put different kinds of ionic compounds on there. In fact, with the capillary, we sucked up a little bit of solution with the capillary and then spotted it, and then we dipped that into a solution, and that solution slowly migrated up the paper and carried some of the solutes, the ionic compounds, up and to certain distances. But this was done by capillary action, right? The water molecules interacting with the surface of the paper, which is also a cellulose. It also has hydroxyl bonds or OH bonds, and so that's how it migrates up. But this so we have these two different forces. We have the adhesive forces, which are the forces holding molecules together, and just like that led to surface tension. But we also have adhesive forces. Those are the properties of the molecules that want to have the tendency to spread out on a surface. So here we have solutions, and they're probably just colored dye water solutions, and so you have the water molecules interacting with the surface in an adhesive fashion and trying to migrate up. And of course you have gravity pulling down, and so the larger the interaction of the surface is, the higher you can go up in the capillary, which is shown here by the skinnier ones. The diameter of the really skinny ones allows more adhesive forces or that water to go up. And so imagine a tree has super tiny little capillaries, if you can call them that at all. And then that's just another third concept that's important. Now let's shift gears and think about boiling point. Okay, so we already know that a boiling point occurs when we have enough thermal energy to break all of the intermolecular forces. However, some of those water molecules, if I'm using that as an example, some of those water molecules evaporate even at room temperature, right? We have measures of humidity. On a hot summer day, obviously it's not hot enough to boil ever, but we do have humidity. That means we have some water molecules that are mixing with the air even at any temperature, and that's because of kinetic motion, right? So we have in a body of water we have molecules that are moving slower and some molecules that are moving faster. And if they have enough kinetic energy and they reach the surface, they can actually evaporate. So some molecules, or water molecules, are always mixing with the air. And we actually used that concept back in the first semester when we dealt with gas laws. We did problems where we collected gases like hydrogen gas over water, and so we had to, if we wanted to use PB equals nRT, for example, to solve for volume, we had to compensate for the vapor pressure that is present, or the hydrogen molecules that are present. And so we went to this chart here. Like if we collected at 25 degrees, we would take that external pressure, let's say it's 760 millimeter mercury, that was the pressure we measured. We would subtract that 23.78, if you recall, to get to the pressure of just the hydrogen gas. And that's because of Dalton's law. Just a quick reminder here, the total pressure is equal to the pressure of the components, in this case the pressure of hydrogen plus the pressure of water. But that's and so the higher the temperature, the higher possibilities of water molecules evaporating and mixing with air. And so you also, of course, have condensation and evaporation happening at the same time, because it reaches an equilibrium, right? You have a rate, you have molecules evaporating, and then when they evaporate, they slow down sometimes, and then they can condense. And so that is at equilibrium. If we have water at 25 degrees and the rate of evaporation and rate of condensation are equal, then we have the same amount of water present. If we increase the temperature, of course, we increase the vapor pressure of water. And when the vapor pressure is equal to the external pressure, that's when boiling occurs, right? That's when the rate of evaporation is higher than the rate of condensation. And so that's when you start seeing boiling. And we do know that the pressure, of course, has an effect on that. For example, you can boil water at a lower temperature at higher altitudes because the external pressure there is lower. So that's just the concept of evaporation. This is an illustration of how many molecules at a given temperature are evaporating. And so we have here the fraction of molecules. So this is a distribution of molecules at different kinetic speeds. And so this is, of course, the mean here. And so you have some, or average, you have some molecules that are slower and some molecules that are faster. And so here in purple at that lower temperature, those are the molecules that are evaporating, that are fast enough to evaporate. And then, of course, if you increase the temperature, you shift that distribution. It becomes not only broader, but you're pushing more molecules into the kinetic speed that allows them to evaporate at that temperature. And so if you push that temperature all the way to here, then you are now at the boiling point. Three, two, one. So I mentioned that at a given temperature, that condensation and vaporization reach an equilibrium. All right, and so we can express that in that the value of the change in enthalpy of condensation is equal to the value of the energy required to vaporize. Right. So just as a reminder, if you stick energy in, right, so you're vaporizing, that's an endothermic process. So vaporization is endothermic. So it has a positive value, right? Energy input. Whereas condensation, that's release of energy, that's an exothermic process. Okay, and so it should have a negative value, right? So if a molecule moves fast and it slows down, it loses kinetic energy given off as thermal energy. and so these molecules have a negative change in energy. But the value, of course, is equal, right? So the energy required to vaporize is the same as the energy released from condensation, right? So if you have a delta H, for example, here's a table. Water requires 44 kilojoules per mole to vaporize. Then the delta H of condensation, of course, would be negative 44.0 kilojoules per mole. All right, and so the units again are going to become very important for all of the calculations that we are performing. For example, if we were to calculate the mass of water that can be vaporized at its boiling point with 155 kilojoules of heat. So we are giving 155 kilojoules of heat, and so the first one we know we are boiling, so that would be 44.0 kilojoules per mole. So I can actually calculate based on that. I can use this conversion factor and say there's 155 kilojoules that are half. Factor dimensional analysis, again important, always write your units down. So you set that up, so you want to multiply by 1 mole divided by 44.0 kilojoules, right? So we are canceling that, but that's not the question. We're not after moles, we are after mass. So we have a second conversion factor we need to use, and that's of course the gram to mole conversion factor. Hopefully you remember. If not, time to review. 1 mole equals 18.0 grams. So now we can convert that to mass. And so times 18.0 grams, 18.0 grams of water equals 1 mole of water. And so of course, to be correct, and this is what I'm looking for. If I ask you to do this on an exam, I am looking for you to set it up like that for full credit, okay? You got to show how all your units cancel. So your moles cancel and your units are going to be in grams of water, which is what mass is, so that is the answer. So different chapter, different concept, but we still are using vector dimensional analysis. Always write your units down, right? So this is just a cleaner version, and also I didn't have memorized how much that is, but that's 63 grams can be evaporated with 155 kilojoules of heat. All right, so this is the end of this part. I'm going to continue with calculations. Go get yourself a Coke and come back.